Good morning. Any questions? Any comments? I want to talk about spin today. Okay. So previously we have been talking about angular momentum, and as you know, angular momentum we talked previously was about rotation in an orbit. Like you have like a central force, and around the central force you have some kind of orbit, and due to this orbit, right, you have angular momentum. But from a classical viewpoint, we know there's a second type of angular momentum, which has to do with like spin, right? Suppose this is the sun, this is the earth. Earth is rotating around the sun, right? That's orbital motion. There's like an orbital angular momentum, and it gives rise to, for example, years and the seasons. And additionally, there is also rotation around, right, its own axis, which gives day and night. And because of this rotation, there's also additional angular momentum, right? This is like a classical viewpoint. So classically, spin is also angular momentum. But quantum mechanically, we have to give up on this idea. Quantum mechanically, people consider this kind of thing for example, electrons, and it yielded nonsense. Like famously, I think the first time people started seeing the result of like spin was, I think, so-called sodium doublet. So sodium had like this famous emission line, which is called sodium doublet, and people could not explain it in any other way. And Uhlenberg and Goldschmidt, who were like graduate students, they considered like an intrinsic spin like this. And I think their advisor was Ehrenfest, and he was impressed, and they wrote the paper, and Ehrenfest asked them to go and ask Lorentz. And Lorentz, being like an expert on relativity, showed them like that's nonsense, right? If you are spinning, and if your angular momentum is like this angular momentum, you are going to get nonsense. And they returned to Ehrenfest, and they said it was like a silly idea. But Ehrenfest said, I already sent your manuscript. You guys are young. You know, there will be many mistakes. It's okay. But it turned out to be they are right? But what we had to give up was like more profound. We had to say that there's no classical analog, and we have to completely abandon classical picture for spin. And we resort to this abstract quantum mechanics. And in the abstract quantum mechanics, what we had this angular momentum algebra. Let me use this compact notation because longer notation we used previously, and we know what we are talking about. It's like Li, Lj. So I and j are x, y, z is equal to I h bar epsilon I j k L k. And this epsilon I j k is like anti-symmetric Levi-Civita, right? It is epsilon I j k. Okay, let me give you like epsilon 1, 2, 3 is plus 1, epsilon 2, 1, 3 is minus 1, and all the cyclic permutations. And whenever any two index is the same, it is going to be 0. For example, epsilon 1, 1, 2 is 0. So if you work this out, it is exactly what we had previously. It's just writing one equation rather than 3. So for spin, we have to abandon the classical picture, and all we need to do is like, okay, we have the same abstract quantum mechanical object. We don't know what it is. Classically, we cannot see it, but we just have to just use this algebra. And people generally use not L for spin, they use S, like this is SI, SJ, and SK. Other than that, everything is exactly the same, right? It's kind of comforting. We don't have to learn anything new. What we learned for like orbital angular momentum is unchanged. And the only thing is like this S in the case of, for example, electron, is 1/2, right? Previously we had L, for example, 1 for like, or 2 all the way up to n-1, but for spin we have like half integer spin for electron. Let me write the algebra. Again, the commuting set is S squared and SZ, and their behavior on the abstract states is like exactly the same, S squared. People generally use this notation. Previously we had L, M. For spin, I'm going to use S, MS. Right? MS is just a reminder, this is like a spin projection. And it's going to be H bar, S plus 1, S, MS. And SZ is exactly the same, S, MS, H bar, MS, S, MS. Right? Like for example, S is equal to 1/2. You can see absolute value of S, which is square root of S squared, is going to, okay, this is H bar squared, is going to be H bar 1/2 plus 1, and this came out to be H bar root 3/2. Whereas MS goes from minus S all the way to S in integer steps. In this case, it's like either -1/2 or +1/2. So the raising and lowering operators are also unchanged. For example, S plus or minus S MS is equal to H bar S plus 1 minus M plus or minus 1 S MS. So these are nothing new. Everything we derived is exactly the same. We just changed the letters to remind us this is a different object. It behaves exactly the same, but its nature is different. Let me give some examples. So from now on, we say spin is intrinsic. The same way charge is intrinsic, right? If I say electron charge is E, nobody goes around and says, is it like some kind of internal dynamical motion? No, it's just E. If I say electron mass is M, you don't go around and say, is it like doing something inside weird? No, it's just mass. And when I say spin, we don't say, oh, is it rotating inside? There's like some, no, it's just spin, some intrinsic quantum number. And every fundamental particle comes with its own spin. We cannot change it. And for example, something called pi meson has spin 0. The most important for us is electron is spin 1/2. Photon is also very important for us. It is spin 1. There are other examples. For example, there's like this delta baryon. It's like spin 3/2. And this is like a hypothetical particle, graviton. Nobody saw this yet. It's like spin 2. Good. Since by far the most important example is spin 1/2, for the rest of the lecture I want to focus on spin 1/2 and see what it behaves like. So let's focus on spin 1/2. So for spin, we have S is 1/2, and MS goes from minus S to plus S, minus 1/2, increase by 1, plus 1/2, and that's it. And the state, now this state is exactly the abstract quantum mechanical state we developed a few weeks ago, and we just said, let's put aside this wave mechanics and let's just consider from like an abstract point of view. And in that view, state is this S, ms, and there are two possibilities. Either I have S is equal to 1/2 and ms is minus 1/2, or S is equal to 1/2 and ms is plus 1/2. But you can see this is kind of awkward to write every time. We know what we mean. Generally, people use a notation like this. So for this one, I may sometimes use up, and for this one, I can use down. And sometimes I also need to like specify it's up with respect to right? Maybe you are not upside down like me. Maybe you are like horizontal. Your reference frame is different. In that case, sometimes I'm going to say this is like z plus. That means up spin around z-axis, and this is z minus. We can use, or people generally use all these notations. Sometimes they mix. So we said this abstract quantum mechanics can be encoded to matrices and linear algebra, right? And once we do that, we don't have to think about abstract concepts. We just multiply matrices, and everything becomes linear algebra operations. So let's also do that. So these matrix representations. So this up along Z, I'm going to, okay, Griffiths is a little bit picky about the notation, and some people are also very picky, like they say that a representation is not the abstract object, right? Abstract object should be separate from its representation. That's fine. I mean, you can do that, but in my opinion, there will never be a case you can distinguish these two, right? Go ahead and just invent some weird font, right? Griffiths is using this like weird sans serif for the representation and usual bold for the abstract object. I don't think it matters. And I also, even if I wanted to, I cannot do it with handwriting. So for me, the abstract object and its representations are the same in quotation marks. So therefore, this up, I'm going to encode it to a vector in the Hilbert space, and I want to call it Z plus, and this is just like a column vector, 1, 0. And similarly, this down state, I'm going to encode it with this chi Z minus, and I'm going to encode it with 0 and 1. And in that case, the most general state in my Hilbert space, right? This is a basis for my Hilbert space. Any other state in my space can be written in terms of these. And for that, like general state is something like A up plus B down. And this thing is going to be in the matrix, okay, this is the abstract object. The matrix representation is going to be Z plus plus B Z minus. This is Greek letter chi. Typically for two component objects we use chi, like it's like we call it spinner. So this is like spinner. The spinner means like a two component object for me. And this thing is going to be, if I put here, it's going to be A, B. And here, A is a complex number. A and B are complex numbers. So since quantum mechanical interpretation is like this is the probability amplitude to be in Z plus state, and this is the probability amplitude to be in the Z minus state, and the probabilities should add up to 1. From here we have the normalization, a squared plus b squared should be 1 before anything else. And now I can like first consider what this s squared operation looks like in this basis. Let's consider s squared. S ms is equal to h bar squared s plus 1 times s ms. So this thing, if I put 1/2, is going to be 3/4. You can see this s square is kind of like an identity, right? It doesn't change whatever I give. It gives the same thing up to a coefficient. It behaves like an identity matrix. Of course, you can do the most general matrix and then work it out, and you can obtain what it is. But I won't do that. Like I can just write you what s square on chi z plus does is h bar squared 3/4 chi z plus, and similarly for z minus. So this is z minus, and what operation does this is like the identity. So I'm going to write s square is equal to 3 h bar squared over 4 1 0 0 1. So this is the point Griffiths is picky. He wants to use like a different notation for this. He says this is the abstract object, but this is the representation, but I can write it with different fonts. Of course, I can use a different letter, and that would confuse us even more, and there would be no point of distinguishing these two. Yes?
Here should the right side should be
Oh yes, you are right. Yes, I think. Thank you. So let me. This way is my. Yeah, thank you. Good job. So the second thing. So I have the first element of the commuting set s squared, and I need to determine sz, and sz acting on s ms is going to give us h bar ms s ms, right? And you can see ms can be plus or minus a half, and you can also work out the matrix in the most general form, but I think writing the result and looking at it is easier. So sz in that case is going to be h bar over 2 1 0 0 minus 1. Right? Just think about chi plus, chi z plus. This is 1 0. If you multiply, it's going to be chi z plus with h bar over 2. And if you consider chi z minus, it is like 0 1. It's going to be chi z minus with minus h bar over 2 in front. So this is the matrix representation of sz. And lastly, we also need to determine s plus and s minus. So s plus or minus s. Okay, let me not write the whole thing again. I think I have it here. So this is what we have. And we can consider cases. If you want to be safe, take your time, slow down, write every case one by one, and try to deduce the matrix form. Like what I would do is like, so S is 1/2, MS is plus a half. Let's start with minus a half. Then this thing, right? This thing is going to be, this is 3/4 minus is plus a half, minus a half, plus or minus 1, and this is going to be, right, this is 3/4 so this is either plus a half. Okay, there are two cases. Either plus a half, or it is 3 over 4. So 1 minus, minus 1 minus 1 is minus 3 over 2 times 1 half minus 3 over 4, or this one, and this one is going to give 1, this one is going to give 0. And from here I see
It should be 1 over 4.
1 over 4, yes, this one is 1 over 4. I think this one is correct, right? Thank you. And this means S plus on, let me call it chi z minus is chi z plus, right? This is what this is the raising S minus on chi z minus. This is the lower signs, and it's going to be 0. Similarly, S plus on chi z plus is going to be 0. I can do exactly the same thing, and S minus on chi z minus is going to be, what is it? If I go from z minus down spin, sorry, this is what? So this is plus, right? Plus minus. So this is z minus, z minus, z plus, z plus. Okay, what am I doing? This is plus. Okay, this is minus. This is what I'm trying to determine. Good. And this is chi z minus. And now you can try to deduce the matrix form, but it is like, that's the nice thing about 2 by 2 matrix, right? You don't have to go around and do algebra every time. You can predict, right? You can guess, and you can fix your guess. It's just two numbers you need to multiply. So S plus is going to be 0, 1, 0, 0. And there's like H bar, because there's H bar here. And S minus is going to be H bar 0, 0, 1, 0. And from here I can deduce what Sx and Sy are. Like S plus or minus was equal to Sx plus or minus I Sy. From here I can say Sx is going to be S plus plus S minus over 2, and Sy is going to be Sx minus Sy over 2i. Now these are matrices. I can sum these matrices and find Sx is going to be H bar over 2, 0, 1, 1, 0, right? Sum of this and this, only of diagonals. And Sz is going to be H bar over 2. Because of this I, it's going to be also of diagonals, but like this, minus I, 0. Yes?
Should Sy equal
Oh, this is... so this one?
yes, in terms of S plus and S minus?
Oh, yes, yes, yes. So this is absolutely, thank you. So this is plus, this is minus, yes. I think this one is correct. Sx, okay, good. Now, all of these things, okay, this is also y. There's like a nice way of writing this using so-called Pauli matrices, and I suggest you get familiar with Pauli matrices because they come out everywhere, right? First, you cannot run away from them. Every time you postpone learning them, you are going to regret because people will bring them back to you. So the second reason is they are very simple. Why would you just not sit down and spend like, I don't know, 10, 15 minutes, learn it for once and for all, right? For the rest of your life, it's going to be with you. And if once you learn it, this spin vector can be written as h bar over 2, this Pauli matrix, and Pauli matrices there are like 3 of them. Sigma x is 0, 1, 1, 0. Sigma y is 0, minus I, 0. And sigma z is 1, 0, 0, minus 1. And they have nice properties. For example, they commute. You can check by multiplying these matrices. Sigma x, sigma y. So they commute like this. 2i, sigma z. And cyclic permutations, exactly like angular momentum. And you can take their square, sigma, right? Square of this matrix, for example, is 1. Square of this matrix is 1. And the square of this matrix is also 1. Sigma x squared, sigma y squared, sigma z squared, they are all unit matrix, 1, 1 in the diagonal. And if you change the order in Pauli matrices, like if sigma x, sigma y, you may want to just copy the same thing and just change the order, something like that. Every time you do that, you just pick up a minus sign. You also check that. So that's also sometimes handy, because we want to change the order of things. You just change and get like the minus sign. And you can do this in the general case. You can have sigma I, sigma j is going to be equal to, if I and j are the same, you have delta ij unit matrix. Otherwise, you have this I, epsilon I, j, k, sigma k. There are more, like you can calculate the exponents of this matrix by using this identity, and there are like more nice properties, but almost everything can be deduced from this set. And we will do that when we need to. So these are Pauli spin matrices.
How did we get the I and the SY matrices when we divide by 2i?
Yeah, let's do that, right? Let's do it. So we have this, like let's consider this. I mean, I always get wrong, but let me try and see. So this is, so sy is going to be equal to s plus minus s minus divided by 2i, right? So this is, let's duplicate. So this is s minus, so this is plus and plus. If I take the difference, 2i sy is equal to s plus minus s minus, and this seems to be correct. Then I need to just take the difference and divide it by, so this sy is difference divided by 2i is h bar, and the difference is like, this is 0, 1, because the second one is minus, this is minus 1, 0. And I want to multiply both numerator and denominator with minus I. So this is minus I. Minus I times I is 1. And I push this minus I inside. This is minus I. Minus minus is 1. This is I. Let's see, did I get it right? H bar, yes. Right, good. Good. Now let's think about what we have done. So notice, we are in SZ basis, right? We are in the basis of SZ, right? There is no particular reason we choose SZ, but typically that's the convention. And what this means is, if you take SZ and put chi z plus here, you are going to get h bar over 2 chi z plus. And if you do it with the other one, you are going to get minus h bar over 2. So this is minus. Right? Or another way to say this is SZ, right? So this is h bar over 2, 1, 0, 0, minus 1. It has two eigenvalues. Lambda is equal to h bar over 2, and corresponding eigenvector I don't even need to calculate. It is 1, 0. Let me also write it. Chi z plus is 1, 0. And the second eigenvalue, lambda, is minus h bar over 2. and its corresponding eigenket is z minus 0, 1. And the most general state, something like A chi z plus B chi z minus, in this basis becomes AB. That's convenient. And the meaning of this is like, let's call this state chi. Chi without any script is the most general state in my Hilbert space. And A and B are complex numbers. And if SZ is measured, what do we get? So if Z is measured on this, somebody prepared this state and gave it to you, and you measure SZ. Right? You either get plus h bar over 2 with probability a squared. You don't get a squared. A squared is the probability, and the result of the measurement is h bar over 2. Right? That's important. Or you get minus h bar over 2 with probability b squared. And since probability should add up to 1, we also have the meaning of this a squared plus b squared 1. Right? Everything just matches nicely. We can also write this sometimes, like since this is like 2 by 2 matrix, you can take Hermitian conjugate. Now it's going to be a row vector. Multiply inner product with chi. This is a column vector, and it's going to be 1. So this one was the easy one. So let's do the confusing one. What about, let's say, XX measurement? So rather than measuring SC, suppose I'm measuring SX. And procedure is the same, right? So SX, we just calculated. It is h bar over 2, 0, 1, 1, 0. And its eigenvalues, right? Again, what are the eigenvalues of SX matrix? Like by using symmetry, right? SZ is just a direction. Maybe I am like pointing my head in a different direction. SX is going to be SZ for me. Then what are the eigenvalues? If eigenvalues of SZ is plus or minus h bar, huh? Exactly, right? They are exactly the same, so we don't need to calculate. Of course, if you are confused, calculate. What is easier than calculating the eigenvalue of this? So what you are going to find is lambda is equal to h bar over 2, or lambda is equal to minus h bar over 2. And eigenvectors are going to be, let me call it chi. Now I put x rather than z. That's why I was carrying this z subscript the whole time. So this is plus, and it's going to be 1 over root 2, 1, 1. You can check, right? Multiply, this is 1, multiply, this is 1, and eigenvalues h bar over 2. And the other one is chi x minus 1 over root 2, 1 minus 1. And now my question was, what if I measure S, not SZ on this given state, but I measure SX? What I need to do is I need to open up this given state in the basis of my measurements. That's our generalized measurement, right? Then this chi, which is equal to AB, should be written in terms of these vectors. And it's also easy to do, right? I mean, I think guessing and then checking is easier than anything else, if you ask me. So this is going to be A over 2, 1, 1, plus 1, minus 1. Now I have the upper column, upper row, and B over 2. So this is 1, 1, minus 1 minus 1. Now I have the lower, right? So just check. 1 plus 1 is 2. That 2 is going to cancel this, and I'll get A. And 1 minus 1 is 0. 1 minus 1 is 0. 1 minus minus 1 is 2, and that 2 is going to cancel, and I have B. But this is what? This is a over 2 chi x plus chi x minus, and this is b over 2 chi x plus minus chi x minus. Now let's combine. Let me finish that and then let's talk. We are going to talk about this a lot. So this is 1 over 2 a minus b chi x plus 1 over 2. Oh, this is, sorry, a plus, and this is a minus b chi x minus. Good?
In the b over 2 term and plus 1, why did we write like minus between the b's?
So because what I am trying to produce here, I am trying to produce something like this. So in the first one, I am trying to produce something like 1, 0, so that if I multiply it with a, I am going to produce this one. I am guessing. Right? For me, guessing is easier than calculating. And in the second one, I am trying to, so this one, I'm trying to produce something like 0, 1, right? 1 minus 1 is going to be 0, 1, and I multiply with b to produce this one. And at the end, I have this term. Now I can use my measurement postulate. And my measurement postulate says, I'm going to, if I measure Sx, I'm going to get h bar over 2 with probability 1 over 4 a plus b. I'm remembering these are complex numbers. And I get minus h bar over 2 with probability 1 over 4 a minus b squared. Good. And because of this, there's also some people want to use this note, like, right, I already introduced you two notations. Like, where did I? So I have this notation, this is one notation, this is another notation, this is like a third notation, and some people also want to use, because of this result, they want to use this one for x. So if you use this means chi x plus, and that means from the above, this is 1 over root 2. I think, did I put the root 2's here? Yes. Root 2, this is up plus down, and the other one is down in the x direction, is going to be chi x minus 1 over root 2, and it's going to be up minus down in the z direction. So as an exercise, for example, if you want to include sy, because in the page, right, this page I have two directions, and maybe you can invent something like for the y direction, you can something like into the page and out of page, and write them in terms of ups and downs, and calculate measurement probabilities of sy on state chi, which is AB. And you will have to deal with complex number I here.
Yeah, can I ask a question? What about probability? Do they change or not?
What do you mean probability change?
We said that a squared plus b squared for sz equal 1. What about for this probability? It doesn't add up to 1.
So this one is always normalized. Yes, A and B, they are always normalized.
What about for, can you move the page?
This one?
Yeah, if we open them up, we don't get 1, right?
Yes, you don't get 1, yes. They are not, right? I think you mean this is not 1 itself, and this is not 1 itself. But if you sum this with this, it is 1 for sure, because it's either up or down in any given direction. There's no other way.
So A and B change, because if we...
No, A and B are given to us. They are constant, complex numbers. But even if they change, later we are going to consider Hamiltonian dynamics, and A and B will be time dependent. Even then, probability will be conserved to be 1. So here, I think I suggest you just open this up, and you are going to see it is 1 given A squared plus B squared is 1. As long as this is given, this is also going to be 1.
But it will be 1 over 2 A squared plus B over 2 A squared.
I think it won't be, right? Let me check. I may have missed a factor here, but I think you are right. Yes, I think there was. Yes. I think this is 2. Now this is correct, right? Yeah. Thank you. Yes, I got 2 here. I got 4 there. Yes.
The above, instead of chi x plus and chi x minus, we should have root 2 times above.
Here.
No, above. If there, so it should be a over 2 times square root of 2 times chi x plus.
So I will write it. Write root 2 here. Where do you want me to write? Here?
Yeah, that line, second one.
Oh, yes. So this is, I see. There's like an overall root 2 here, and overall root 2 here, there, right? Yes, good job. Now we came to the crux of this thing. I want to make a little discussion and finish it there. And that's the most important thing about quantum mechanics. And that's the nice thing about spin a half. You can, right? People, I don't understand. People want to go to like heavy mathematics, hoping that they are going to understand quantum mechanics. No. I think you need to cut mathematics out of quantum mechanics, because mathematics does not help, in my opinion. And the simplest way to do this is spin a half, right? Here's your spin a half, and it's going to tell you the most confusing part of quantum mechanics. And here's the scenario, which I have enough time. Suppose somebody gives us up spin, right? This is z direction up spin, and there's like a question. And the question is, what is z component of given spin? So what is the z component of this given spin? Right? Exactly, right? This is given. Answer is h bar over 2, and this is 100%. There is no ambiguity, because it is given. If you measure it, every time you measure it with SC, you are going to get h bar over 2. So this is certain. So there is no confusion about this, but the question, exactly the same question, but rather than z component, I am asking what is the x component of this upspin, right? So the answer, what is the answer?
H over 2 of minus H over 2. With some probability.
Yes, anybody have any objections? So that's exactly the answer you shouldn't give, okay? That's exactly what everybody says, and the answer is, this question is nonsense, right? Nonsense. And the correct question is, like, let me also cite you the correct question, because in quantum mechanics, we don't know what it is, right? We only have measurements. And we can have measurements, and we can predict outcomes of measurements. What something is internally, we cannot talk about that. So that's the critical part. So rather than that, if I measure x component of spin, what do I get? So this is the correct question, and any other question is nonsense. Right? We have to. Why do we have to do this? Because we have to abandon classical realism. Classically, something is there, and we measure it. Quantum mechanically, we have to give up on that. Okay? think about this. And the answer to this more meaningful question is, I get, because this up spin is given, and this up spin we just calculated is combination, right? Combination of here, combination of this and that. And the answer is, I get h bar over 2 with probability 1/2 and minus h bar over 2 with probability 1/2. And lastly, suppose I did this second measurement x and I found, like question, like I measured Sx and I found h bar over 2. Does this mean this single electron had h bar over 2 spin along x direction prior to measurement? So did chi, this chi is like did spin, or this did electron have h bar over 2 prior, right? This is the keyword, to measurement. And what do we say that, right? I measured, right? Previously I didn't know. It was either h bar over 2 or minus h bar over 2, and I did the measurement, and now I found h bar over 2. After the measurement, I know what it is. But now I'm saying, like, because I get h bar over 2, does that mean prior to my measurement, the electron had h bar over 2? Right? So people will keep asking to you. This is also a nonsense question. The answer to this question is, I think you can check this, unperformed measurements have no result. Because what does it mean prior to measurement? Prior to measurement means no measurement. No measurement means no result. Okay? That's very simple, but it takes a little while to accept. And last thing, and I will finish after this. Now, I was given h bar over 2 in z direction. I measured, right, x direction, and I found h bar over 2. Previously, it was h bar over 2 in the z direction. Now, after my measurement, it's h bar over 2 in x direction. Does it mean that I know both z direction and x direction simultaneously? Because, right, it was given, and I did additional measurements. What do we say to that? So, question, and this is last question. So, after Sx measurement, do I have h bar over 2 along z and h bar over 2 along x? What do we say? No, right? Because your wave function collapsed, your previous wave function is gone. So now you have still h bar over 2 with probability 1/2 along sz, and similarly minus h bar over 2 along sz with probability 1/2. Okay? So measurement plays a critical role. Measurement is like is not some gimmick. Measurement is part of the theory. And now people will ask you, and you will also ask yourself, how can this be, right? The realism is realism independent of our measurements, some people say, but it seems like we have to abandon that. Good? All right, thank you.